Is material selection for nuclear applications. Nuclear applications have a wide variety of different fields and uses, from hydrogen production to seawater desalination, to even the more common just nuclear power, electrical power, energy production, with the future being bright and vast. So what really important characteristics are defined in nuclear material selection? Well, we have the conventional properties such as density and modulus. But we also have the specific nuclear properties that are very important, such as the nuclear cross sections, attenuation coefficient, and radioactive resistance and permeability. These properties are very specific to nuclear applications, however, not decreasing the importance of the conventional properties most engineers consider daily. So what is really the problem with this is most current material databases really only focus on the physical or chemical properties of materials like ANSI's Granta. And while some nuclear property databases do exist, they haven't been cross-linked. They're not entirely exhaustive of most common engineering alloys and their isotopes. And furthermore, we're lacking the fundamental data on these nuclear properties on a large scale to actually produce such a database. So what do we really need to do to fix this? Is, well, obviously a comprehensive database of the physical, chemical, and nuclear properties formulated either into a software or online tool would be entirely fundamental and perfect for such a problem. And these would need to include all the properties, not only for every engineering alloy, but also for their elemental isotopal constituents. This being due to that the physical and chemical properties we commonly consider are driven by the electronic structure or the structure of the electrons in the atoms, versus the nuclear properties are focused on the actual nucleus of the atom, or the protons and neutrons, and thus we need to consider the isotopes. So what kind of vision do we actually want to see in this? Well, we'd love to see property data maps for the various materials, alloys, and their isotopes, as you can kind of see on the right here, with continued expansion into new engineering materials, properties, and their alloys, and formulating this into some sort of computer software or tool index for evaluation. So we examined 3 particular case studies: accident-tolerant fuel forms, nuclear fission fuel forms, and fusion blanket coolant materials, and how this type of tool or database could fundamentally work or operate and improve the process.
So the first case study we're going to look at is accident-tolerant fuel forms, which is just another way of saying, does the material stand up to accident conditions of nuclear reactors, such as high temperature and high pressure? In the specific case study, we are looking at the material for the cladding of fuel rods. In the picture on the right, you can see that the cladding is just the surrounding material of the fuel pellets. This material prevents corrosion from the coolant and also prevents the release of fission products into the coolant. Some of the requirements for this material is that it has a low Gibbs energy for oxide formation, high stiffness, and they're resistant to the fission products. Currently, zirconium alloys and some stainless steels are being used, and these meet the requirements under normal conditions, but there is no option for a material that meets the requirements under nuclear accident conditions. So how do we go about the selection for this material? The first thing we want to look at is the melting point. So we want a material that has a high melting point, but a low cross section for neutron absorption. As you can see on the figure on the right, at the top, zirconium and silicon are very close to each other, and for its family of materials with low cross section, it has the highest melting point. But if we want to increase that melting point, perhaps we would take a look at a material such as molybdenum. The one problem here is that this has a higher cross section, which means higher neutron absorption. So we need to decrease that cross section. By decreasing that cross section, we now yield stress now comes into play. We have to make sure that the material is strong enough. Ultimately, all of these requirements are bound to each other, and we need more and more property maps. So this is where a nuclear property database would come in and help. It would help synthesize all the requirements into one property map for optimization. And we could also take a look at other nuclear properties, such as Gibbs free energy values as a function of temperature, which would help predict corrosion properties of the alloys under temperatures under accident conditions, as well as we could take a look at different isotopes. Specifically for molybdenum, molybdenum, different isotopes of molybdenum have different values for neutron absorption. This means that we can revisit molybdenum as an option, since now we can play around with that cross section since we have the availability of different isotopes.
Another case study we wanted to look at involves a material selection process for safer and more effective nuclear fission fuel forms. So to give a little bit of background information, majority of the world's fission reactor are fueled using uranium dioxide pellets. These fuels are required to maintain good mechanical and chemical properties under very harsh operating conditions. It has a long list of material requirements, include but not limited to things like high melting point, low neutron cross-section, and high uranium density, and so on and so forth. The current fuel form excels in a great number of areas, but it has a relatively low uranium density and low thermal conductivity, hence limits the efficiency of the reactor. Therefore, the most straightforward approach is to maintain what it does well and look for options that would improve upon its shortcomings. Two of the examples presented in the case study are listed on the right. The figures of them are listed on the right. One correlates the melting temperature to uranium content of the material to identify alternative material that would that provides a comparable melting point but greater uranium content. The second example, the bottom graph, tells us alternative material with better thermal conductivity while maintaining comparable thermal stability with current material. This case study again demonstrates how material selection for nuclear application can be greatly simplified with the integration of a comprehensive nuclear property data on top of existing electron-based properties. Especially given that in the case study, although not completely covered, many more neutron and proton-based properties needs to be examined for the candidates are required for us to give the final selection. A good example would be the ongoing research on the fabrication process and a composite fuel form. Researchers must be able to model thermal and neutron cross sections of a uranium dioxide and molybdenum composite as a function of volume fraction to devise appropriate weight ratios and manufacturing processes.
And finally, we look into the material selection for fusion blanket coolant materials. So a little bit of background on blanket coolants. Fusion blankets surround the vessel in a fusion plant, absorbing energy from neutrons and then using that energy to drive a turbine that then produces electricity. The main coolant material used today within these blankets is lithium, which reacts with the fusion neutrons to produce tritium, which you can see here on the figure on the right. Some common material requirements for these coolants are suitable thermophysical properties. They need to collect fusion energy from neutrons, as well as breed enough tritium to make the system tritium self-sufficient. So when selecting these materials, obviously we need to find materials that have high tritium breeding ratios and energy multiplication rate. Like I mentioned on the previous slide, lithium is the widely used material, but it is also chemically reactive. So we look into lithium alloys that are less reactive, but this could also take away from other necessary criteria for these coolants. And then looking into this graph on the right, with effective cross-section on the x-axis and effective Q value on the y-axis, this Q value is basically the average energy generated by all possible nuclear reactions. We can see that lithium is placed pretty well on this graph. Some of these other materials like silver, gallium, copper, they may be a little bit more expensive, a little bit harder to use, which is why we tend to stick to lithium. How would a nuclear property database help us here? It would be a lot easier to discern performance of materials in a nuclear application. Other properties such as structural stiffness, surface temperature, they rank pretty highly of value. So comparing these materials would be very nice. And going back to creating a self-sufficient tritium system, It needs to be done in a very efficient way. So using this data in the previous graph, which is more effective, more based on simulation, may not be as accurate as if we had a proper nuclear property database. And some conclusions and limitations we came to, there's certainly value to developing a full nuclear property table database and tool. It would severely improve efficiency and cost effectiveness. However, it's largely prohibitive to measure these nuclear properties, and it's very costly, and it may not be optimal to release such properties and such critical information to nuclear engineering. And thank you.